Okay, let's begin. So I want to talk about this model selection problem. So there's a lot of different model selection problems, and so this is probably the most common one that you'll encounter. But basically a model selection problem is to select between two models. So let me just ask a quick question. How do you select between two competing models? And I'll call these M1 and M2. And I don't think I need to tell you anything about the models, but if you'd like, I could say maybe this is a linear regression with normal errors, and maybe this is a linear regression with different covariates in it, and it has t-distributed errors. Or you can change them to any models you'd like. They're different. They could have different distributional forms. They could have different covariates, but they're different. Somebody comes into you with a data set, says, I've got these two competing models. Which one do you like better? Now you answer that question.
Cross-validation.
Cross-validation. Okay, so you're going to do a holdout sample. You're going to fit both models. Then you're going to look at your predictive something, or maybe you compare to your expected values in some way, and you check error rates and you cross-validate. So yeah, maybe something like that. That could work. Could be a little bit problematic that if I have only, so I'm writing down, I've got n data points. Imagine I ended up knowing the variance, so I'm making up a fiction right now, and n was equal to p, and I tried to do this sort of thing. It'd be very difficult to do. But Annie's got a technique, and that tool can work, and it's some tool that some people run off to do, but it can be deficient as well. So if you're not data rich, you're going to have a problem cross-validating. I kind of like it. So Annie didn't see how she's going to fit her models, so maybe she's a Bayesian, maybe she's something different. She can play around with the way she fits and still use this procedure. So that's kind of cool. It's kind of flexible so long as you have enough data to do it. Any other answers? There's lots of answers to this
one that's
question.
more mathematically tractable.
Find the one that's
Easy.
mathematically more tractable. So, Dan, what does that mean?
Just things that are easy to compute, right?
I
Easy
love
to
it.
program.
Yeah, absolutely. Forget about all this stuff. So, why do I need that model? Let's just compute this using, let's try to fit this thing using y bars. Forget about all the data. Don't even use the x's. It's easier to just throw them all away. If you fit that model and you just plugged in intercept, your intercept would be y bar. So there is a balancing to that. You want the most parsimonious model that also explains your data. And so I kind of like that. We want to come up with a simpler explanation of the data, but they have to well explain the data at hand. How much variation there is in the y's, one such metric. There's other metrics. So parsimonious. So that's a quality we'd like in our model selection techniques. What else? I like that. We'll use that everywhere. So I think all good model selection techniques will tend towards the simpler model if two models equally explain something. Tend towards the simple model. So that's a good principle. What else would you do?
AIC corrected.
AIC corrected. Okay, so now we're getting into a real model selection tool. So what we usually look at is we look at the likelihood ratio. So there's a precursor to this. So the likelihood ratio. And if you prefer, I could call it this thing right here. So I could maximize my parameters. So I'm just going to say theta. These are just my arbitrary parameters. Maybe I'll use beta or something like that because I've written down my model in terms of betas over here. So beta in model 1, likelihood. and then I divide by the maximum. Look at the betas in model 2. I look at this thing right here. So we'll come around to the suggestion of AIC correcting this in a moment. What do we know about this ratio? Know anything about it? If you've taken a regression class, you should know a ton. If you're a statistician and you don't know much about that ratio, I'm going to assume you haven't taken more than one statistics class. What do we know about that? So when I maximize it and I throw in the maximum likelihood estimates under the two models, this likelihood might represent very different things. So if model 1 was Gaussian and model 2 was T, well, these likelihoods would have totally different forms, Joel. So I can distinguish that. But I could look at that thing. If maybe my likelihoods were built on two regression forms like this, or maybe model 1 looks something like this. I'll just write it down. Model 1 was yi is equal to xi3 beta 3 plus xi 17 times beta 17 plus error. Model 2, I'll write it up here, look maybe like this. yi is going to be, I goes from 1 to 10, xij, beta j, let's change that to a j, plus j goes from 25 to 29, xij, beta j, plus n. So maybe these are two models. So I could certainly maximize those two likelihoods. I could write down the likelihoods for those two models. If you can't do that, go back to your previous homeworks. You did it over and over again with regression models. And I could maximize those things, and I could even figure out in closed form what the maximum likelihood solution looks like. What does that look like? It looks like those things up there at the top of the board. X transpose X inverse, X transpose Y, where I'm reformatting that X matrix, depending on the covariates that I'm using. Then I can compute this. Does anybody know any statistics concerning this ratio?
Is it an F distribution?
What's that?
Is it the partial F test?
Yeah, so it follows some distribution, right? It's got some distribution to it. And so in this case, right here, you'll notice that these two models right here are nested. i.e. both of them are nested in this full model right here. So I might call this the full model. Where P is going to be some number bigger than 29. It could be very, very big. And so that's going to have some sort of, if I take -2 logs of this thing, so if I look at this, -2 logarithms, in these nested cases, this will follow a chi-squared distribution. And so that's kind of cool. And so, but there's some real problems with using this sort of framework. We look at how well something fits. Again, let's go to the case where n is p. And so if n is p, you've got a big problem. And so you'll perfectly fit everything. And so it'll look very, very good to you in terms of fit. So keep in mind, those maximum likelihoods are fit criterions. How well does that model fit the data? And so if you haven't known this, if I have n data points and I build in some sort of n-dimensional polynomial into this, I can perfectly fit everything. And so that can be really problematic. As I add more and more parameters into the model, I start to fit better. And so these criterions tend to support bigger models, if you just look at them. And so what the suggestion is just to add a penalty, plus penalty. there's a whole bunch of different types of penalties. There's some that account very well for sample size. There's some that account more and penalize more for dimensionality. AIC is one of these things. The Ikeke, how do you say it? So, Japanese guy. And there's also the Bayesian criterion, the penalty. There's a whole bunch of assumptions that go into these things when you use one versus the other. What they mean in terms of Bayesian modeling. And so, but basically we can look at some sort of max likelihood ratio and then penalize it accordingly. So that's one such way to do this. So all of these techniques that we're kind of talking about are trying to penalize the dimensionality, going back to what Dan and JD said. So we're trying to reduce the dimension by kind of knocking out some of these variables right here. So we've got tools to do that. Let me show you some other ways to do this. So the problem with kind of this setup is I need to consider every possible model and compare them to each other. Nobody's ever going to do that. So let me just ask this. In terms of this problem, how many nested submodels are there?
It's like 2 to the n or 2 to the p.
2 to the p is the answer. That's a big number usually. And so you probably wouldn't want to compute every model and compare them to each other. Saying that, if p were like 10 or 20, you could do it. So, and I would probably say go ahead and do it. But there's a lot of algorithms that are out there that try to prevent you from computing these 2 to the p different models and doing a comparison. I'll also point out that this criterion, this thing, -2 log max likelihood ratios, if I'm not dealing in the nested case and I don't have normality in everything, I don't know if that's chi-square distributed at all. It could be something else. And so a lot of people will look at this and they'll say it's chi-square distributed, but they'll be working in non-nested cases. And so I need nesting to induce that chi-square distribution. I need normality, or at least asymptotic normality. So maybe you can do this using a generalized linear model and have that sort of asymptotic normality kicking in for you and get these chi-squared results. If you're not working in the nested case, this statistic doesn't mean anything. And so if you're comparing two non-nested models, like in my example, t versus normal, that has nothing to do with chi-square distribution, that statistic. And so this is just kind of a convention people go and run after, but it's unclear what big is and what small is. Okay, so this has some deficiencies. I'm surprised nobody said Bayes factor. This thing kind of looks like a Bayes factor. I could come up with a Bayes factor, right? So let's just write that down as a competitor to compare models as a Bayesian maybe use Bayes factors. So what does that thing look like? I integrate over this thing. I'm going to have some prior on my betas. I'm going to be specific about calling this model 1. And I just look at my likelihood function over my model parameters in my other model, given my data, and I integrate over my prior on model 2. Which betas? The betas in model 1 versus the betas in model 2. So I look at the Bayes factor. I don't love Bayes factors simply because I can't tell what big and small is, so I always do this other thing. I'll take my Bayes factor, and I'll compare it on a probability scale. So this is going to be the probability of model 2, or I should say model 1 compared to model 2. This is 1 plus 1 minus pi naught, pi naught. So this is the probability on model 1. This is the probability on model 2 times Bayes factor inverse, inverted. That's how I move to a probability scale. And now I feel like, oh, this is a tool that I've been at least trained on, thinking about things between 0 and 1. So that's maybe how I might compare using this sort of calculation. We've talked about all the deficiencies of doing this different ways. I could have used p-values too. Maybe compute, looking at some corresponding p-values.
If we take the ratio of the Bayes factor to the maximum likelihood ratio, would we normalize it in a certain way, or would that be completely wrong?
Normalize what?
So you're saying that in order for you to know whether Bayes factor is big or small, you're converting it into a probability just so that we know the size of it. But I'm saying that if we do take Bayes factor and divide it by the maximum likelihood ratio, would that kind of normalize it?
The maximum likelihood ratio for what? The full model?
Yeah, so we take this ratio and divide it by the maximum.
It would normalize it, but in a way that I don't understand at all.
Okay.
I don't know any properties of that normalization scheme. So probably because it's different in every case. You can try it out. I'm going to guess that that distribution isn't well governed, but it's certainly some normalization. I just don't know what it means. So I think this is at least putting it on some scale that we understand, at least. Okay, so let's just talk about some possibilities for dealing with this particular model. What I want you to understand is there's a lot of stuff that we can do. We're going to disagree for the same reasons why we might disagree over p-values. And those sort of things is, how far away from one of these betas being 0 do we have to be before I'm willing to kick it out of the model? So that is the question. So if I want to think through nested models, I'm thinking about cases where these beta j's, these coefficients right here, are zeros. And so that is exactly our sharp test that we're talking about. So this comes up all the time. So all that sharp testing stuff and model selection, they have everything to do with each other. So model selection and hypothesis testing are in a lot of ways governed by the same stuff, arguing over the same stuff. Here's a common tool. So let me just ask a question first. If p were less than n, what would you do? Very classical setup. P's less than n. Just before I ask for what you would do, can you think of an example where this might come up? You ever seen a problem like this? I mean, you can imagine them in your head right now. It's, which covariates do I go and collect? So somebody says, try to explain what's going on in Y and go collect some stuff that explains it. Where do I stop? Collecting things. You can collect an infinite number of things that are not predictive about Y. So, but where are some typical problems where this arises?
It's like almost everything, right?
Yeah, man. It's like almost everything. So where do we see this in science applications?
Like predicting the growth, like height, weight, correlation.
So what would all your covariates be?
I would say you've got, yeah, like age, height, weight, and then you're trying to map or maybe like a binary one for gender, and you're trying to map the population.
Yeah, so maybe.
Human growth over time.
Yeah, maybe we could just put in all these human attributes and just start building them all in. I've taken all these measurements, I want to use them. So genomics is a place where this happens a lot. So a lot of times we'll go in and we'll measure somebody's genome, and you've got 6 million base pairs. So that's an X vector, 6 million dimensional for every individual. So you're going to need over 6 million individuals to get on top of this problem. Does that sound right? So good luck. So not going to happen. So what do you do in these sort of cases?
Wait, so in that case, you're saying that N is the...
Number of individuals. And the P is the number of genes that I measure.
So
Okay, so in that case, it's
the
experiment,
experiment.
right?
Oh!
In that case.
Yeah, my goodness gracious. I see why you're confused. Let's do that. Shake off the cobwebs. Okay. So let me go back. No, not almost every case. Almost every case I think that you could consider more things you can measure about each individual. Usually we stop for practical reasons. You think about a scientist during the 1930s. It's like, you want me to measure something about this flower? I can only measure like its petal length and width. That's all I can think of. So, it used to be small, like just a few things we would measure, but nowadays with computers we measure everything. So in genomics there is this big phenomena where you've got big P, small p. So what do?
Bootstrap?
It may be bootstrap, but it won't get you anywhere. So every time you bootstrap and try to find an estimate, your estimate is not going to work out. What's going to happen in this thing up here, x transpose x inverse, x transpose y, I want you to think of what would happen if the X matrix was this big p-dimensional thing and it only had a skinny n number of individuals. And I ended up taking x transpose x and I tried to invert it. It won't invert. So what's the rank of that matrix?
At most N.
Yeah, at most n. And so that's right, that's a good way to say it. I probably would have made the mistake and said n, but at most n. If those things are correlated with each other, that's going to knock out another rank. So that's going to be not full rank, and you're not going to be able to invert the matrix. So if you go to bootstrap, you're going to crash on the first iteration. Bootstrapping will not save you here. Bootstrapping induces variance for estimates. And so it doesn't help you decide on what your estimator is. It helps you to build variance around an estimate.
Can you do PCA in this case, because you're running the same problem?
Yeah, so PCA is a solution. So I could look at a reduced dimension, I could project it into a reduced dimensional space, and then I could fit my regressions there. Typical technique. So PCA is a solution. If you don't know what it is, I guess that's okay, something for you to learn about. So, principle, component analysis.
Same as SVB?
Yeah.
Yes. Absolutely. It's the SVD sort of solution, right? Project through a couple principal directions. What else?
Most biologists use like a pre-screening. So
Maybe a
they,
pre-screening.
like run key univariate models, see where it's significant, and then reduce.
Yeah, I guess people will do this sort of stuff where they'll marginalize out everything. The only problem with this can be huge is that if things are correlated with each other, if the X's have influence on each other. And I think in genome-wide studies, a lot of times they do.
That's the most popular method.
So I know people will do that, and maybe that's something you'll do if you just don't know what to do. But my goodness, that could give you a train wreck of solutions. So I don't know if I'm in favor of that. So another technique is ridge regression. Let me show you this one. It's easy. This goes under a couple different names. It's called a regularization technique. So, ridge or
Lasso.
lasso's different. I'll get to that in a moment. So, lasso has a different penalty. So, ridge or Tigranov regularization. It's a typical way. I don't know how to spell it though. So, or L2 regularization. So that's a whole bunch of different names. So here's the typical problem. Tell you what these things are. This is just my y vector. This is my x matrix, x11 to x1p, down to xn1, xnp, and the betas would be beta 1, delta beta. Okay, so this is your typical solution. It induces this. So you can do some calculus and figure that out. So here's ridge, or I'll say L2 regularization. So it looks like this. Minimize over beta, y minus x beta in the 2 norm. So what I mean by this right here, just to be entirely clear, is I'm just looking at y minus x beta transpose y minus x beta. So these are just squared residuals. I'm taking the sums of these things. It's just sums of squared residuals. Some people call this least squares problem for that reason. So if you take this over in an optimization community, we'll talk about minimizing the squared errors. In statistics classes, we want full distributions over everything. And so we end up doing Gaussian regression, and we come up with at least the same point solution. So we'll come up with that. But of course, if p is too big, you're not going to be able to invert that matrix. So what people will do is they'll say, let this be subject to a constraint. Sum of the beta j's, j goes from 1 to p squared, let it be less than some tolerance. So let's just think about what this does. If c is small, it's going to start pushing these betas towards 0. That's what it does. It starts scrunching them. Anybody tell what this shape is right here? What's the shape of this thing? It's a circle around 0. And so I'm really scrunching the betas in this circular fashion. So the way I'm drawing it right here is 3-dimensional, and I'm squashing that sphere.
So that's a second order cone constraint.
Yeah, if you'd like. So sounds good to me. So this has another way. You can write this down and you can solve this using calculus. Notice everything is squared in here. I could have written this down right here is beta transpose beta less than c. Same sort of thing. So everything's in a quadratic form. So calculus applies. So this can be written like this. Rewrite it. I can write this down. Minimize over beta, y minus x beta. Just squaring out the square root over the top. That's what I'm doing here, so that they're all on the same scales. So plus lambda, if you will, times beta norm. So all this is beta transpose beta. That's all I'm writing down there. So I want to minimize this thing. And so how did I rewrite that? How did I do that? What did I do exactly?
Optimization.
Yeah, so what is this technique called? This is the Lagrange multiplier.
So this is the Lagrange relaxation.
Yeah, so. So this is related to C, but it's not C. So there's some optimum for C right there. There's going to be, something that gives me good predictive performance. So I might say, I want C to be something really, really small right here. But if I start kicking out too many of the variables, or I squash them down towards 0 and make them really, really tiny, I might be squashing stuff that explains the Y. And so I might use cross-validation to figure out what C is, or my corresponding Lagrange multiplier, lambda. And so, how do we learn this? Typical answer might be cross-validation if I had enough data to do that. And so, that could be difficult though. So one problem with this answer right here is I don't get exact zeros in my betas. So I'm squashing them. But remember, this thing is kind of a circle right in here. And so the way I'm squashing stuff doesn't have any points on it. So if you're into optimization theory, how do you get something and you drive it down to 0? You usually want to develop a contour constraint that has an edge at 0. And this one is smooth there. And so if it does push it to 0, you just got lucky. So probability of 0 of that happening. And so I will write down as a Bayesian this is equivalent to choosing your prior pi beta. This is going to be equal to, I'll just write it this way, proportional to e to the minus 1/2 beta transpose beta divided by sigma squared, and I'll write lambda up there. You could consider this right here one parameter. I have to scale everything to sigma squared to give it the equivalent Bayesian solution to this other thing right here. So this is just Gaussian prior. So these are this is a key dimensional normal prior centered at 0. And maybe I could maximize the posterior under this prior.
But if we're reducing the values of beta, but not actually eliminating values of beta, don't we still have a problem with p squared and n?
Yeah, so in this case, you don't. Right here, we'll look at the solution. And so long as lambda is finite, it actually gives you a full ring solution. Let's just work through the math and see what the solution is. You can probably see the correspondence between this and this. Let's just write down what the Bayesian is doing and answer JV's question. So, work through this posterior distribution. This is going to be proportional to e to the minus 1/2 y minus x beta transpose y minus x beta divided by sigma squared. That was my model there. I'm saying I know it for now. You know what I'll do. If I tell you you don't know it, I'll say go ahead and estimate it. Change everything from normals to t's. Times my prior. E to the minus 1/2 beta transpose beta lambda over sigma squared. This is just e to the minus 1/2 y minus x beta transpose y minus x beta I'll write it like this. I'm going to pull the sigma squared out. So sigma squared in front of everything. I'm going to write this down as beta transpose lambda I beta. So I just rewrote that a little bit. So shove that lambda right in the middle, and I decided to multiply by the identity. You'll see why I did that in a second. can just rewrite this, e to the minus 1/2 sigma squared, y transpose y, that term doesn't tell me anything, minus 2 beta transpose x transpose y, there were 2 of those in the cross term, plus beta transpose x transpose x beta, plus beta transpose lambda I beta. That's everything. I'm going to combine these 2 terms. So this is going to be beta transpose x transpose x plus lambda I beta. Now I'm ready to identify what my posterior expectation is. That's going to define my regression line. You'll notice this plus that right there is this thing. This is this. Identical to each other. So they're the same. So think about what a Bayesian does. Usually we like to maximize this thing. This is a probability distribution, so I want to maximize the probability distribution. It's a function of my unknown. So get my map estimator. And here we're minimizing residuals. This is a minimization problem, but we usually do maximization as Bayesian. But I've got a negative out in front of here. And I've got a monotonic function. And so I've changed my maximization problem to a minimum. And then working with the monotonic function right there, I didn't perturb where that local minima is. So they're the same problems. So this is just the way you write this down as a Bayesian. Some people call this Bayesian ridge. You get the whole posterior interpretation out of everything. So sometimes people like some of the old estimators but want Bayesian interpretation. So I can start measuring my intervals and saying what I think is in them. Those sort of interpretations. And so what's the solution to this? Beta hat, I'll call it ridge. What do? I look at my -2 linear terms. There it is. And I multiply it by the inverse of this stuff. So my variance is right in here. It would get multiplied by this. So we'll cancel each other out. But if you will, this is going to be x transpose x plus lambda I invert. And if you'd like me to slide the sigma squared, I could put it in there. But I'm just going to have them all cancel each other out. X transpose y. Now let's go to JD's concern and see, did we just mess up and invert something we're not allowed to invert? This is still rank reduced. What's the rank of this? This is a beautiful thing right here. Just add some diagonal mass and it fills out the rank of the problem. And so from a Bayesian perspective, that's my prior coming in. And so it acts as a constraint. So priors are constraints. So if you like constraints in your models, you might be inclined to be a Bayesian and write it down that way. It doesn't really matter which way you approach this problem. It's Bayesian or non-Bayesian. You're just going to argue over what you called things, but your solutions are going to work out exactly the same. So there's another solution to this problem. I'll just write down the downside here. Downside is beta hat ridge won't have zeros. You could start putting things as close to 0 as you wanted to, but it's not actually going to have a 0 in there. So you might want zeros. This solution does have zeros. Very similar.
Do you use 0 norm instead of 2 norm?
Use the 1 norm.
1 norm? Oh.
Same model setup, minimize, beta, subject to, I'll write it like this. Beta j absolute value, j goes from 1 to p, is less than some constraint. This problem is harder to work with. So you can't do calculus. I can't come up.
Check your norm. You still have 2.
What is it?
The first one is still the least squares problem.
Yeah, this is least squares, so this is squared error.
Well,
And this is absolute value, that's the whole point. So the other one had a 2 right here. You might have been bringing that 2 over here. There's no 2 here. So I'll just be really clear, raised to the 1. That's absolute value. What is this shape? Right here? Yeah.
That's the technically cross polytope.
Yeah, exactly. You guys know more about this stuff than I do. I call it a square. So it's a diagonal. It's a little diamond. So it has edges at 0. So when the maximization function starts traversing up those contours and it catches that edge, it'll start pushing it down. So I'm not going to prove that to you, but most of you that know about working in simplexes and what they do when you're optimizing will understand that. But basically the edges that intersect the 0 axes are ending up going to induce zeros. So if you end up looking at the solution to this, you will get zeros in the betas depending on how hard you constrain it. So if I start constraining this more and more and more and I make C smaller and smaller and smaller, I'm going to start pushing everything towards zeros. How do you decide which C to use? Maybe cross-validate. That's a typical solution. Here's the Bayesian corresponding solution. The Bayesian lasso uses P beta. I'll just write it down like this. For each j, it's going to be proportional to e to the minus lambda over sigma squared, if you will. Just come up with the exact Lagrange multiplier equivalence. Beta j absolute value. So my constraint is now my prior in a Bayesian solution. So I can get zeros in all of this. It's kind of cool. And so does anybody know what distribution this is?
It's called like a 2-sided exponential or something?
Yeah, maybe a double exponential. So this is called a double exponential. There's another name for it. Some people call it the Laplace distribution. I call it double exponential usually because it exactly tells us what it is, kind of. So, but that's what it is. It has a spike over at 0. Those spikes give us the actual 0. So what does this thing look like? It's like this. Spike at 0. Those little pointy things right there are what induce the zeros. So if the solution gets close to those points suck them all the way into zeros. It's kind of a neat thing. So there is a little bit of a problem with this solution that if you grew up in the 60s, you would never be able to get the solution. So you need to run an optimization algorithm over this to do it. So I'm not going to talk about any of the algorithms that people use for this. You could maybe do MCMC or something like that in a Bayesian framework. Except for the Bayesian finding maximums out of that can be a little bit cumbersome. So I just want to leave these as possible solutions, but they're kind of heuristic solutions in a lot of ways. Just kind of smashing the betas down. And so I haven't really mechanistically said what's happening. I get a convenient solution out of everything. So I can induce rank by putting a 2 there, by putting a 1 there, I can induce zeros. So parsimony. And so it turns out, in my experience, if I simulate out of a true model, it's pretty well regulated, and I use the lasso thing and I cross-validate, I'm usually right about 80% of the time. It's not bad. Pretty good, simple, cheap solution. What I want to show you is another competitor. So here's what I'm going to show you next time. Next time, we'll look at MCMC using point mass priors. So I'll say this is going to be my prior on the null, which is going to be beta j is equal to 0, plus my alternative mass times some other prior. So I'll write this down, aj, right here. This is going to be on beta j. I'm probably going to center this thing at 0, and then I'm going to have some alternative variables. And you're going to have to choose that one for all the reasons I've already told you. So same exact setup. This is that null hypothesis testing setup. So I can use this as well. We're going to put a prior on every beta. This kind of has a nice solution you end up getting out of it. While you have to do a lot of computation to finally fit your model, it tries to figure out the joint associations in all of the parameters when you're moving through everything. And there'll be some correlation between the parameters that you get to check. And so that your model mixes through. And it tries to come up with the best coherent model. So there are deficiencies to all of these solutions, but this one is my favorite one so long as I can well calibrate this right here. I want to point out something that we didn't talk about, is that in our x's, did we standardize them or not? And so if we didn't standardize them, and I started using the ridge solution or the lasso solution, my penalty is acting differently on all the covariates. And so you might be inclined to standardize everything before you throw it into your model. It depends on what you're doing. But if I did standardize everything in my regression setup, then I probably have good rationale for picking this parameter right here. I might pick it to be 1 standard deviation. So what I want to show you is how Gibbs sampling works to click through these models in such a manner that at the end of every iteration of my MCMC, I have some new model with updated betas in it. And my posterior frequency of seeing particular models will converge to my posterior probability of that model being good compared to all my other competitive models, all my nested models. So, and it's going to involve computing the Bayes factor, which is the downside. But if I can compute that, if I end up picking pi h alpha to be normal, I can compute it in closed form. And so basically, I'm just going to be flipping coins after I compute the Bayes factor into a posterior probability. And I mix that in some big Gibbs sampler, and everything works out. I'll show you the details of that next time. I think that's it. So lots of solutions for the model selection problem. I usually encourage you to check them all out. So if you guys want some more extra credit, I'm going to say you can do this for another 5% extra credit. Set up a simulation step. You don't have to make it that high dimensional, maybe 10D or something like that. And so if you want to get started on that and do some ridge and do some lasso, get that stuff implemented. There's packages for it. Just push the button, get the solutions out of it, and then I'll ask you to code this thing. And then see how well this works compared to everything else. I think you'll be surprised how different things all do. That's it for now, guys. Thanks a lot.